Yes, sir.
Okay. So in the chat box, I have given the question again. And before that, see, you can see here in page number 57, right? In page number 57, when the Bayard number is less than zero point 0.1, we know the significance of Bayard number. Okay. What is the significance of Bayard number? What is Bayard number actually? Is it visible first?
Yes, sir.
Yes, sir.
Okay. What is the significance of Bayard number? If the Bayard number is less than zero point 0.1, then we can assume it as a lumped parameter system. Okay. If it is in between zero point 0.1 to 100, or then we can assume it as a infinite solid. Okay. If it tends to infinity, then it is semi-infinite solid, right? So this is what we have assumed, right? Bayard number less than zero point 0.1, Bayard number greater than zero point 0.1. Okay, so similarly here also, here if you see it, uh, transient conduction Fourier number greater than zero point 0.1, okay, infinite solid. Hmm? And Bayard number will be again, it will be also greater than zero point 0.1, and it will be less than 100. uh, so then we can say it as a we can assume the solid as an infinite solid, and we can proceed the problem. Okay. Now this formula, the temperature expression, I have already derived this T minus T infinity by T naught minus T infinity, e power minus HA by rho Vc into tau. We know that, right?
Yes, sir.
Am I correct or
Yes.
not?
Yes.
Yeah. And there is one more term which is said to be time constant, which I will be discussing after solving the problem. The time constant is usually given by it is the inverse of this, right? HA by rho Vc, instead of this, rho Vc divided by HA is nothing but time constant. Okay. And what happens is, why we have to find out this time constant, we will discuss about that. Before that, please tell me. I heard one of the student he has solved this problem. How he solved it? Can you explain how you solved, ma? Who's the guy?
Yes, sir.
Please tell your name.
It, Ram.
Ram Kishan. Huh?
Yes, sir.
Yeah. Yes, Kishan. Go ahead.
Yes, sir. First, we calculate the so let's calculate the LC value first, where LC is equal to V divided by AS.
Okay.
And then I calculated for the Bayard number, which
See.
came around.
Yeah. Mm.
Oh, okay, sir. It came around 0.0536.
Okay.
So
Very
it's
good.
less than 0.1.
Yeah. Definitely. Then it is a lumped parameter system. Okay. Fine.
So
What
then
is?
the formula that we saw just now in
Yeah.
the data book, we
Yeah.
saw for the tau value,
Okay.
and the
See, it's
tau
made
value
of
came.
steel, right? It's made of steel.
Yes, sir.
Okay. From where you got the steel values?
Uh, Data book, sir.
Which page number?
Um, sorry, 1 second, sir.
Steel here. You have carbon steel. Uh, Let me check it out. Chrome steel, carbon steel, cast iron, silver is there, stainless steel is there, tungsten steel is there. Which one you assumed? So that's what I have given this question also, right? And you can assume, right? It's your assumption. Suppose if you assume it as stainless steel or silicon steel, okay, so the value changes. All of you are able to see this, the density.
Yes, sir.
Okay, suppose if you assume it as silicon steel, the density is 7417, and alpha is 5.5 into 10 power minus 6, specific heat capacity is 460, and thermal conductivity is 19, right? Okay, so suppose if you assume it as stainless steel, then it changes again. And suppose if you assume it as carbon steel, you can see carbon steel, then again you have change in values. Okay, so the thermal conductivity value changes between carbon steel and this what's that nickel steel or silicon steel. Okay, so you can see the silicon steel thermal conductivity is 19, whereas the carbon steel, it has got thermal conductivity, higher thermal conductivity of 36.3. Okay, so when you assume, right, when you assume carbon steel, right, so you will be having increase in thermal conductivity. Okay, so it's a depends upon what you take. Okay, so it's up to you. Okay, that's what there comes the role of the engineer, right? um, you have to decide, okay, which one. See, you may ask a question, sir, whether I take carbon steel and I proceed the problem, is it wrong, sir? No, it's correct only. See, it's up to you, you have to assume it. Okay, and you can see here the carbon steel with AISI 1010. You can see here 7832 and 434 and 63.9 higher thermal conductivity and higher specific heat capacity. Right. So it's up to you, students. Which one you have assumed? That's why that's my question, Ramkishan. All of you are able to. All of you are listening.
Yes, sir.
Yes, sir.
Yeah.
Yes, sir.
Yes, Kishan.
Yes, sir.
Which one? Which one you have taken? That's my question. How many students are there? I don't know.
Sir, I assumed for carbon steel.
Carbon steel. Which one? First one or second one?
Um, in my book, there's only like one, the first one, which shows on the top of the page.
7854. Is it correct?
Um,
Top of the page. At the top of the page, we have aluminum.
oh no, no actually, no, sir. It's the density is 7833.
Okay, then it is carbon steel AISI because you have 7832 here. Okay, no issues. Let me take it out. See, students, all of you are able to understand. See, when a question is given like this, okay, if the k row value were not given, okay, so if it is mentioned, see, if suppose if it is mentioned as copper, as in the previous question, right? In the previous question, it was mentioned as copper, and I have the liberty to take the pure copper value. Am I correct, student? I think I have
Yes, sir.
taken the pure copper value in the problem.
Yes, sir.
Am I correct or not? Yeah, I have
Yes,
taken
sir.
8954.
Yes, sir.
Yeah, right, in the previous problem. So this is what makes you right. It's not only about studying formulas. Okay, no need to study formula in the subject because I have given you the Eden Master as a data book. You have got the data with you. You have to take the appropriate values and you have to use the correct formula and you have to get the result for that particular problem. Is it fine? Numerical.
Yes.
Is it right? Okay. Let me start. Okay, ma. After doing this, I will discuss about time constant also, right? Because time constant is there in the data book as well as you have to understand what is the purpose of time constant, studying time constant. Now, one of you please tell me from the data book. Please tell me the values, ma. Rho and C values, rho C and K values. What is density? What is the density, ma?
732.
7833.
7833 kg per meter cube.
Yes,
Units
sir.
are very very important. Okay, what is the thermal conductivity?
43.6.
Thermal conductivity. Okay, 53.6. Very good. Okay, what about the CP value, specific heat capacity?
465.
465, sir.
465 joule per kg Kelvin. Am I correct? Joule or kilojoules?
Joule, sir. Joule per
Joule
kg
per
Okay,
Kelvin.
kg Kelvin.
okay, man. Now we know that. So now we have got this. The cylindrical ingot is 10 centimeter in dia and 30 centimeter length. We know that characteristic length L, which is equal to or L suffix C. What is given in the data book? LC, L suffix C or L? Page number
Uh,
57, I think. Yeah. So it's given us EL only, right? L is nothing but the significant length or the characteristic length. Actually, characteristic length is the correct term which we have to use, which is nothing but volume by area. And it is also mentioned for cylinders, spheres, and for flat plate. It is mentioned, right? So we know that L, which is equal to, or L suffix E, which is equal to volume by area, which is nothing but R by 2 for cylinders. You know that how you get it, right? Volume.
Yes, sir.
What is the volume?
So pi r square.
And the area is so pi gets cancelled, L gets cancelled, 1 R gets cancelled. So you have R. So R by 2. Is it fine, students? Is it
Yes,
fine?
sir.
Okay, now the diameter is 5 centimeter, sorry, 10 centimeter, radius is 5 centimeter, and so the characteristic length will be equal to R by 2. So 5 into 10 power minus 2 divided by 2, that is 2.5 into 10 power minus 2 meters. Okay, is it fine?
Oh yes, sir.
Yes, sir.
Okay, now we know that. Now look into the question now. H value is already mentioned here, 100. You have to take it 100. The furnace gas. Furnace gas is nothing but 1250 degrees, and initial temperature of the steel is 90 degrees. What is the time? Okay, the ingot must reach a temperature of 800 degrees C. What is the time needed? Okay, so that's what the question is. So we know that T minus T infinity by T naught minus T infinity, which is equal to e power minus HA tau divided by rho Vc. Okay, and what is the initial temperature? Initial temperature is 90 degrees. Okay, and surrounding fluid temperature is, since the furnace is the one where you will be having um, high temperature. Okay, high temperature zone of 1250 degrees. Okay, so T T is what is the temperature that it has to reach? It has to reach 800 degrees. Yeah, am I correct?
Yes, sir.
T equal to 800 degrees. T naught initial temperature is 90 degrees, and surrounding fluid temperature is 1250. Am I correct?
Oh yes, sir.
Now
Yes, sir.
substituting this equal to this one. Substituting this, you will be getting 90. Sorry, 9. It's not 90. 800 minus 1250 divided by 90 minus 1250, which is equal to e to the power. I'm writing on a smooth surface. One kindly, please excuse me. 100 into tau divided by, so a by v, it's nothing but inverse of v by a. Okay, we know that it is inverse of v by a. Am I correct? Am I correct, students?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Inverse of v by a is a by v. So uh, now rho, what is the density we got from the data book? 7833, right?
Yes, sir.
Density is 7833. Substitute 7833 here, and R by 2 is 2.5 into 10 power minus 2, 0.025.
Yes, sir.
And what is the final thing? C value, specific capacity, 465.
Yes, sir.
Am I correct?
Yes, sir.
So now you can find out the time. How much seconds? Take log on both sides and get the value. All of you are able to do it. See why you are taking this much time. By this time, I might have completed. Or otherwise, if you want me to add this also, take natural log on both sides. Okay, so natural log of 800 minus 1050 minus 450 divided by 90,160. Yeah, minus minus gets cancelled, which is equal to 100 into tau divided by 78. Please correct me if I am wrong. How much you are getting now? Four,
Sorry,
six.
862, sir. 862.332.
Who's the guy
Yes,
who
sir.
completed it?
862.33.
So the final answer, time seconds you are getting is final answer. Tau, how much you are getting?
862.33, sir.
Same, sir.
Seconds. Okay, students, all of you got this. Please check your calculators.
Yes, sir.
Yes, sir.
Please check it in your calculators, man. Please check
Yes,
it in
sir.
your
That's the
calculators
value.
because taking log on both sides and substituting the values, please check whether you are getting 862. Okay, so like this you have to solve the problem. Now I have already told you about, there is one more thing. All of you have taken it? All of you have taken this? Students?
Yes, sir.
Everyone?
Yes, sir.
Vishwapriyan, Achyutan, Adityan? Taken?
Take it.
Everyone? Hello?
Yes.
Okay. So now there is one more term which is said to be time constant. Okay, even in the data book we have seen that, right? Time constant equal to tau c, time at which t minus t infinity divided by t naught minus t infinity, which is equal to 1 by e, right? 1 by e or e power minus 1. Okay. So e power minus 1. See, now when this e power, you will be having e power minus 1 here, t minus t infinity by t naught minus t infinity, which is equal to e power minus ha by rho vc into tau. If the tau is equal to rho vc by ha, then you will be having minus 1. Am I correct? I
Yes, sir.
don't know. See, why you people are blinking? I don't know. See, the expression is, what is the expression? T minus t infinity by t naught minus t infinity, which is equal to e to the power minus ha into tau divided by rho vc. Am I correct?
Yeah, yes, sir.
Okay. Now this expression, okay, this expression, if it has to become e power minus 1, that's what given here. If tau equal to tau suffix c, time constant is the time at which, okay, t minus t infinity by t naught minus t infinity equal to 1 by e. Is it visible to you?
Yes, sir.
Yes, sir.
Okay. Now, when this become minus 1 means, if tau is equal to tau c constant, which is equal to rho vc by ha. Okay, so in the place of tau, if I substitute on the right hand side e power minus ha by rho vc, and if tau equal to tau suffix c into rho vc by ha. So ha will cancel, rho vc will cancel, and you will be having e power minus 1. Am I correct? Am I
Yes, sir.
correct or not? Now, please tell me the value of this e power minus 1. What is e power minus 1?
0.368, sir.
0.36.
368.
368.
Okay, ma. Now, why we are finding out this time constant is, one important thing which we have to understand is, see, there is especially in temperature measuring devices. Can you give some examples for temperature measuring devices, ma? In lab, we conducted 4 experiments, ma, up to last week. Which is the one which measures the temperature? A thermocouple, right? A sensor, right?
Yes,
A
sir.
thermocouple, K-type thermocouple. Okay. Now, can you define what is the response time of a thermocouple? What is the response time of a thermocouple? Anyone? Anyone? No one knows. Students? See, actually, the response time or response of a thermocouple is nothing but the time needed or the time required for the thermocouple to attain the source temperature. See, we have the thermometers. When you go to doctors, especially when you are sick, when you are having fever, okay, uh, what does the doctor do?
Check your temperature.
Yeah, okay. How much time he will keep it in our body? Below, that is, he will be keeping it in below tongue, right? How much time he keeps it? How much time seconds?
About a minute. About a minute.
Yes,
Almost a minute, sir. 60 seconds.
almost a minute. Some of the doctors they used to keep it for more than 2 minutes. Why? Why they are keeping it for 2 minutes? Because it's very much connected to this, the response.
Sir, it should attain a steady temperature.
Yeah, it should attain steady state temperature. Very good. So the temperature keeps on increasing for the first few seconds, and then it reaches a temperature where it remains constant. Okay, so the response of the measuring device or the response of a thermocouple is nothing but the time needed or the time required for the particular thermocouple or any temperature measuring device to attain the source temperature. Okay, now what is this advantage of having finding out the time constant? See, the advantage in finding out the time constant is, see, now what happens is, I have already told you about response time. There is one more term which is known as sensitivity of the instrument. The sensitivity of the instrument is nothing but it is the time needed, uh, whatever measuring device it can be, whether it can be thermometer or electrical resistance thermometer or whatever it may be, or thermocouple, whatever it may be. Okay, the time needed by the measuring device to achieve its 63.2 percentage of the value of the initial temperature difference. Okay, 63.2 percentage of the value. So what it is here is, we know that t minus t infinity by t naught minus t infinity, when this value is e power minus 1, which is equal to 0.368. Okay, 0.368. Okay, so the temperature difference at the given instant is equal to 0.368 of the initial temperature difference. This is initial temperature difference. Am I correct? T naught is nothing but the initial temperature of the solid. T infinity is nothing but the surrounding fluid temperature. And after some time t, okay, this is temperature at the instant small t is this capital T. So t minus t infinity is equal to 0.368 8 times of the initial temperature difference. Okay, the temperature difference at a given instant is 0.368 terms of the times of the initial temperature difference. Okay, now when we want to talk about the sensitivity, okay, so for example, if we talk about the sensitivity of thermocouple, then it is nothing but the time required for the thermocouple to reach its 63.2 percentage of the initial temperature difference value. Okay, so now what is that 63.2 percentage, you may ask me? 1 minus 0.368 is equal to 63, sorry, 0.6632. Am I correct?
Yes,
Yes,
sir.
sir.
Okay, so that's why this time constant tau suffix e is very much important. Okay, so the lower the value, the lower the tau suffix c value, okay, the faster will be the uh, sensitivity of the instrument, or the time needed. What I said earlier, there is one more definition which I said. The response time will be as less as possible. Okay, smaller the tau suffix e value. All of you are able to understand? Smaller the tau suffix e value, the faster will be the response time. What is the response time? What is the response time? Hello, students. Am I audible? Am I audible or not?
Yes, sir. Yes, sir. Yes.
What is the what is the response time? It is the time needed or the time required for the measuring device to attain the source temperature. Okay, so when this value when this time constant value approaches, okay, 0, or if it is very lesser, okay, then naturally what happens is you will be having or in other words, this one also, even in other terms, when this h by rho vc approaches 0, or if the value is very less, then naturally what happens is the response time of the instrument is very less. Okay, the response, it will quickly respond to the changes in temperature. Is it fine?
Yes, sir.
Yes,
So
sir.
you have to know one thing. One is response time, the other one is sensitivity of the measuring instrument. Okay, so these two things are very important. Okay, so that's why the fourth problem I have given like that. Okay, the an average heat transfer coefficient of is it visible to you?
Yes,
Yes,
sir.
sir. Visible.
Okay, again I have given copper, so you can tell me now. See, this is what you are expected to state the assumptions. An average heat transfer coefficient for flow of 90 degrees a year over a flat plate is measured by observing the time history of a 40 thick copper slab exposed to 90 degrees C air. Okay, suppose if the air is instead of air, if some other medium is given, for example, liquid sodium or liquid potassium is given, then you will be expected to find out. Okay, because the H value changes, right? The H value changes for liquid metals, the H value changes for water, the H value changes for gases, the H value changes for air. Okay, am I correct? Convective heat transfer coefficient value changes for different fluids. Am I correct or not?
Yes, sir.
Yes, sir.
Okay. Now it was mentioned as the copper slab, which is of 40 thickness, it is exposed to 90 degrees C air. Okay. In one test run, the initial temperature of the plate was 200 degrees, and in 4.5 minutes time, the temperature decreases to 35 degrees. Okay. So find the heat transfer coefficient in this case, and you should state your assumption. So what is the first assumption you can take? What is the first assumption you can take? Please tell me. Tell me faster. Time is running out. Which assumption you will take, ma? Hello? Am I audible?
Yes, sir. Yes, sir.
All
Yes,
of you are
sir.
there? What's happening? You have any test today, or anything you have to do today? Any assignment or some other thing? Yes?
No, sir.
Okay, then what is the assumption you will be taking? What is the assumption, Ma?
List.
So you will be assuming it as semi-infinite solid or infinite solid or lumped system. Please tell me.
Lump.
So under the assumption of lumped system, okay, under the assumption of lumped system, we will be proceeding the problem. Okay, so assuming the plate, copper plate is placed in an environment which is at a very high temperature, and assuming that the internal resistance offered by the conduction or the conductivity is very much lesser when compared to the convective resistance. Okay, I have already told you what is Bayes number. L by Ka divided by 1 by Ha, right? So what is this
Yes.
numerator? What is this denominator? Theory is very, very important. It's not up to numericals, whatever you solve. Okay, theory is very, very important. What is this Bayes number? What is this numerator? What is this denominator? Achyutan?
Conductivity divided by.
Huh? Conductive resistance by convective
Convective
resistance.
resistance.
Okay, so assuming the cooling process is Newtonian cooling. Okay, Newtonian cooling process is the process in which the internal conductive resistance is almost negligible or very small when compared to the convective resistance. Okay, so assuming Newtonian heating or Newtonian cooling, we proceed the problem and we will be getting the solution for this. Okay, is it fine? Is it fine
Yes,
or
sir.
not?
Yes, sir.
So
Yes, sir.
now it is a copper. Okay. So from the first problem, please tell me what is the rho value, Cp value, and K value for copper.
So raw value 8954 kilogram per meter cube.
Okay. What is capital C? Specific capacity.
It's 383.
383.
And thermal conductivity is 386 watt per meter Kelvin.
So we got the values. Am I correct, students?
Yes.
Okay. So now the thickness is 40 mm. The thickness is given as 40 mm. So L equal to thickness divided by 2. So it is 20 mm, 0.02 meters. Am I correct?
Yes, sir.
Yes.
Okay. Now substituting this, what is the initial temperature of the gas or T infinity? T infinity is initial temperature of the plate is T naught is 200. Okay.
35.
And T infinity is 90 degrees here. Okay. And final
Sorry, 90.
temperature T equal to 35 degrees. It has to from 200 degrees C. Oh, the temperature decreased by. That's what I was wondering. The temperature decreased by 35 degrees C. Okay, so 200 minus 35, ma. Please understand. So the air is at a temperature 90 degrees C. So T infinity is 90 degrees C and T naught is 200 degrees C. Okay, so from 200 degrees C, it reduces by 35 degrees C. So how much T?
165.
165 degrees C. Okay, so just like me, please don't do mistakes. Okay, so T equal to 165, T naught is 200, and T infinity is 90. So now substitute. Sorry, 165 minus
90, sir.
H. H is the one which we are going to find out, right? Am I correct, students?
Yes, sir.
Yes, sir.
Okay, what is the tau time in seconds? It is 4.5 minutes. So 4.5 into 60. Am I correct?
Yes, sir.
And density 8954. Substitute and get me the result. And volume, area by volume by area is L 0.02. So 1 by 0.02. And what is the CP? 383. What is the convective heat transfer coefficient? Take log on both sides and find out H. Take a log on both sides. Find out what is the value. What is the value, ma? How much? All of you are there.
Oh, yes, sir. 1 minute.
Yes, sir. Yes, sir.
Saurav, what is the value?
Yes, sir. Doing it, sir. Doing it, sir.
You have only 1 hour time for a cat, right? You have to solve two or three numericals.
Sir,
And you
H value is 97.2, the 97.5.
97.3, sir. 97.3.
97.28, sir.
watt per meter square Kelvin. Okay. So if your problem is given like this, you have to solve like this and carefully read the temperature decreased by 35 degrees. It's not decreases to 35 degrees because the air is at 90 degrees. Okay. So when 200 degrees plate is exposed to air at 90 degrees, it will be in between 200 and 90. It won't become 35 degrees. Am I correct? Am I correct or not?
Yes, sir.
All of you have calculated this.
Yes, sir.
Yes, sir, getting the same value.
97.3. Okay, so similarly, try this fifth one also. Fifth one is so simple. Okay, you can try this, the same thing. Okay, flow of air at 28 degrees C over 12.5 diasphere. Okay, so instead of cylinder, if you have sphere, your radius divided by 3 is the characteristic length. Again, it is a copper ball, and you have two thermocouples. Okay, both the thermocouples resist the same temperature at the, and in one test, the initial temperature was 65 degrees, and it is decreased by 11 degrees C, not decreased to. Please understand. So from 65 it reduces to how much? Is it visible?
Yes, sir.
Is it visible?
50, sir.
So first furnish initial temperature T naught is 65 and temperature T is 54. Am I correct?
Yes, sir.
And T infinity is 28 and 1.15 minutes. So 1.15 into 60, you will be getting the tau value. And what is the assumption? So again, the assumption is we are assuming it as a lumped parameter system, and using the lumped parameter analysis, we will find it out. Okay, students.
Yes, sir.
Okay.
Yes, sir.
Only thing
Yes,
is in
sir.
the previous problem r by 2, here r by 3, right? Am I correct or not?
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay, ma. So in addition to this, I want to say a few things to you. Okay, in the very first unit, is it visible to you, all of you?
Yes, sir.
Yes, sir.
Okay. In the very first unit,
sir.
you will be having very simple problems. Okay, like this. Okay, you will be having a theory and you will be having a combo of problems. Okay, the problems involving, for example, yeah. So you will be having thickness of the wall given, thermal conductivity K will be given, inner surface temperature will be given, and outer will be given, and energy dissipated Q will also be given. So you will be asked to find out what is the determine the area. Yeah, so we know that Q equal to minus Ka dt by dx. So from that, when you substitute it, you will be getting the area. Am I correct?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so this type of small problems. Say I didn't want to solve the small problems. Q equal to minus Ka dt by dx, Q equal to Ha delta and all. I didn't want to solve it. That's why I didn't solve it. Okay, but in module one we have only 3 hours duration, and in that 3 hours you have the theory. Okay, where we studied the conduction theory, and suppose if they ask the temperature gradient, then what you will do in the same problem? You will be finding out what is dt by dx. Dt by dx after getting the area. After getting the area 0.759, you substitute here dt by dx, which is equal to q by minus Ka. Am I correct? Am
Yes,
I
sir.
correct or not?
Yes, sir.
Yes,
So
sir.
even in the second example, if you see that they have, I think it's not there in this textbook. Yeah, in the first. So as per Fourier law, we have found out what is Q. Q equal to minus Ka dt by dx. Suppose if you are asked to find out the temperature gradient, then dt by dx equal to this one minus 700 degrees C per meter. Is it fine? Is it visible?
Yes, sir.
Yes, sir.
All of you.
Yes, sir.
I don't know. Those who have missed
Yes,
the
sir, visible.
classes, today's classes, I don't know. And similarly, we know that convective heat transfer coefficient is Q equal to Ha del T. So if surface temperature is given, for example, this one. Okay, so hot plate dimension is given 1 meter by 1.5 meter. So area will be 1 into 1.5, 1.5 meter squared, and it is maintained at 300 degrees C. So T is 300, and surface temperature is 300, and T infinity surrounding air temperature is 20 degrees, and H value is 20. So naturally, Q equal to Ha del T. Is it fine? You can substitute and you can get the result. Okay, whether it is a cylinder or whether it is a sphere or whether it is a flat plate. Is it fine, students?
Yes, sir.
Yes, sir, fine.
And
Yes.
similarly, the second problem is also the same one. In case the area becomes, in case of wire, it is nothing but the surface area pi dl. So you have to find the surface area and then you have to find out the q. Is it fine? See, I didn't want
Yes,
Yes,
to
sir.
tease the small numericals and all. When you go through it, you can see that. And similarly, when you talk about radiation, I have told you the Stephen Boltzmann law. You have Kirchhoff's law, you have Wien's law. Okay, Wien's law, which states that lambda max T is equal to a constant, or lambda, the wavelength is proportional to, inversely proportional to the absolute temperature. The absolute temperature should be substituted in Kelvin, and Stephen Boltzmann law, what it says is Q directly proportional to T power 4, or Q equal to F into sigma into area into T1 power 4 minus T2 power 4. For example, if one body is at 1000 degrees C, then the other body, if it is in 30 degrees C or 40 degrees C or 100 degrees C, whatever it may be. Okay, if the temperature difference between the two bodies is greater than 100, then you will be having heat convection by radiation also, which depends upon shape factor. Okay, whether it is a square, cylinder, or round, or whatever it may be, shape factor F. Sigma is nothing but the Stephen Boltzmann constant, 5.6 into 10 power minus 8, which I already told you. Area is the area of the plate, which is given in meter squared, and T1 and T2 is nothing but the temperature in Kelvin. Most of the students, what they do is they will be substituting in degree C, 1000 degree C if it is given. So you have to convert it into Kelvin and you have to substitute. Okay, so like this, you have one or two problems. Okay, where you will be having the F value which is given in the question. That is the value of factor due to geometrical location, and emissivity is 0.52. So you can substitute it. Sigma value is 5.67 into 10 power minus 8, and area 1.5 meter squared. And here you can see here, and maintained at 300 degrees C, and another surface is at 40 degrees. So the 300 degrees C is converted into 573 Kelvin here, and 40 degrees C is converted into 313 Kelvin. Okay, you will be you can substitute. No need to do this step. Okay, you have the calculator. 0.52 into 5.67 into 10 power minus 8 into 1.5 into 573 power 4 minus 313 power 4. Is it fine, students? Is it fine?
Fine, sir.
Okay. And finally, there is one more
Yes.
problem where you have uh, that is Q conducted, which is equal to Q convected plus Q radiated. Okay. So that is the heat energy conducted by the solid is given to the surrounding fluid, and due to the temperature difference between the fluid and the solid, you will be having radiation loss. Okay, you will be having convection heat loss, you will be having radiation heat loss. Okay, so this gives you the energy balance. Okay, so even here also the very first step which we found as you can see here, what is the very first step which we did in this problem? Yeah, HA del T, which is equal to MCP dt divided by small dt. Am I correct? This is the energy balance. Heat transfer in the body during given time is equal to the increase in energy. The heat is transferred into the body or into the atmosphere. It is given by the convective heat transfer. Okay, and this temperature gradient within the body or rho Vc density, uh, the volume of the body. It so this particular expression we got it by the energy balance. So the same energy balance is used here. Heat conducted through the plate is equal to convective heat loss plus radiation heat loss. Okay, so this type of small things you will be given in module 1. Okay, and similarly how to find out the dt by dx temperature gradient. Okay, so this type of small problems may be given or it may not be given also. Okay, it's up to you. But I am saying this, why I am saying this, because try to go through that also, right? So with this I stop and try to solve the fifth problem, and in tomorrow's class, okay, we will discuss in detail about infinite solid. Okay, so in infinite solid what we will be doing, and we will be depending upon Hazel's chart to solve problems. Okay, whether it is a flat plate, cylinder, or sphere. That's why I have restricted only three problems. Okay, one for flat plate, one for cylinder, and one for sphere. Okay, and the third problem is very very important. Okay, because it involves two concepts. Okay, one is lumped system, the other one will be. Uh, this is a problem which I have taken from Sachdeva textbook. Okay, so what happens is earlier it will the solid is cooled in water, and then it will be cooled in air. Okay, so cooling in water, you will be getting Bayes number less than zero point 0.1, and cooling in air you will be getting Bayes number greater than 1.1. Okay, so it is a combo problem, combination of infinite solid and lumped parameter system. Okay, one cooling, it is lumped parameter system. The other one will be uh, what's that? Infinite solid. Okay, so we will be discussing about that in the next class. Is it fine?
Yes, fine, sir.
Yes, sir.
Okay, let me stop the recording at this time. And one